The checkpoint serialization format defines the binary layout used to persist runtime state at designated intervals. All checkpoints conform to version 3 of the specification, which maintains backward compatibility with version 2 through a feature flag mechanism. The format begins with a 16-byte header containing magic bytes, format version, timestamp, and a CRC32 checksum of the remaining payload. Following the header, the checkpoint contains a variable length metadata section. This section includes the system uptime at serialization time, the current transaction sequence number, and an inventory of all active data structures. Metadata is encoded using a length prefixed string format, where each field is preceded by a 4-byte unsigned integer indicating its byte length. The state payload follows immediately after metadata. State is organized into blocks, each corresponding to a distinct subsystem. Block boundaries are marked by a 1-byte delimiter and a 4-byte size field. The order of blocks is deterministic and established during system initialization. No interleaving of blocks is permitted. Within each state block, individual objects are stored using a tag length value encoding scheme. The tag byte identifies the object type, the length field specifies the byte count of the value, and the value contains the serialized object data. Tag values are registered during system bootstrap and must not change without version increment. Numeric values within the checkpoint use big-endian byte ordering exclusively. Floating point values conform to IEEE 754 double precision representation. Strings are encoded with a 4-byte length prefix followed by raw UTF-8 bytes. No null terminator is appended. The maximum string length is 2 GB. Complex collections, such as maps and arrays, are serialized with an element count prefix. Maps enumerate key-value pairs sequentially. Arrays preserve insertion order. Empty collections are represented by a 0-length count field. Recursive or self-referential structures are flattened into a linear representation using depth-first traversal. The checkpoint payload concludes with a manifest section listing all serialized objects by identifier. The manifest contains a count field followed by sequential entries. Each entry stores the object identifier, its block location, its byte offset, and its serialized size. This enables random access recovery of specific objects. Recovery from a checkpoint proceeds in phases. The first phase reads and validates the header. If the magic bytes do not match the expected value, recovery aborts immediately. If the version number exceeds the system's supported maximum, recovery also terminates. The CRC32 value is verified against the payload before deserialization begins. The second recovery phase deserializes the metadata section. The system verifies that recorded transaction sequences do not exceed the current sequence counter. If a forward-pointing reference is detected, the recovery process logs a warning and adjusts the counter upward. All recovered metadata is written to a temporary in-memory buffer. The third phase reconstructs state blocks sequentially. For each block, the system allocates memory according to the recorded size and populates it from the checkpoint stream. If a block's declared size does not match its calculated size after deserialization, recovery logs an error and skips to the next block boundary. Objects within each block are deserialized according to their tag type. Tag handlers are invoked in order of object appearance. If an unknown tag is encountered and the version flag permits backward compatibility, the handler skips the value and continues. If the version does not permit skipping, deserialization halts and an error is returned. The manifest section is deserialized in the final phase. The system builds an index mapping object identifiers to their in-memory addresses. This index is used to resolve any internal references that may have been stored as identifiers. If an identifier in the manifest does not correspond to a recovered object, a verification error is logged. Incremental checkpoints store only changed state since the previous full checkpoint. The format includes a changed type field for each modified object, indicating insertion, deletion, or update. The manifest in an incremental checkpoint references the prior full checkpoint by timestamp. During recovery, incremental changes are applied sequentially in timestamp order. Checkpoint compression may be applied to the entire payload following serialization. Supported algorithms are deflate and LZ4. The header compression type field indicates which algorithm was used. If compression is enabled, the header includes an uncompressed size field for validation. Decompression occurs before any deserialization. Checkpoint files are stored with a timestamped file name pattern. The pattern is checkpoint emd.hmmsseq.bin, where seq is a monotonic counter. A metadata directory maintains a JSON index of all checkpoints, including their size, creation time, object count, and compression status. This index is updated atomically after each checkpoint completes. Garbage collection of old checkpoints follows a retention policy. Full checkpoints older than 30 days are deleted unless no newer full checkpoint exists. Incremental checkpoints are deleted when their corresponding full checkpoint is deleted. The garbage collection process executes asynchronously and acquires no locks on the active checkpoint stream. Deletion is logged to the maintenance audit trail.